So hi Alicante, hola, and I'm not Kevin. Yeah, so there was a change in the schedule and I have a talk for you about signals. Kevin still has his amazing talk tomorrow. But yeah, so now we're going to talk about what the heck are signals in the end and what do they mean. It's not exactly a React talk, but it's a framework agnostic talk. So hopefully with that you will understand what are the trade-offs of signals and then why React doesn't have them and etc. But first of all, like who am I? My name is ATILA and I work as DevRel lead at this company called Crab Nebula. We work a lot with Tauri, which is a framework for building desktop applications and mobile applications with web technologies. I'm also a Google developer expert in web technologies, and I work in the Solid Developer Experience team, which is why I talk a lot about signals. I am in way too many social media to the point that then I need to create redirects from my own website so I remember what are my handles there. So you can find me there if you have any feedback or questions after this talk. And so I know this is a React conference, but I would like to know, like, which ones of you have experience with any of the frameworks that have signals at any point? Can you please just raise your hand so I know who I'm talking to? Yeah, okay, so a few. Awesome. So for the ones of you who have never worked with signals and perhaps never really looked into them, my experience in trying to explain signals, the conversation usually goes like this. So we say, oh, signals, and then what the heck are those? And then somebody says, oh, fine-grained reactivity. And they're like, cool, those are words, but what the heck are those? Those are signals. And then you get into this loop where everybody just takes these for like, okay, these are things now, and we do it, and it's like use state, but not quite, and so on, and you just move on. So we're going to dissect those, like what are signals? They are actually not even all the same. So before we get started into diving into what are signals, we need to talk a little bit about API architectures, because signals need to live within some kind of structure in order for them to work. And the decision about which structure you're going to use is going to affect your ability to have a reactive system or not. So mainly and fundamentally, there are two ways of structuring your APIs. One is pull, where you request for the data, and if the data is there, you get it. And the other is by push, when the data source is going to push the data towards your client, towards the client. So let's do a little exercise about how a pull system works. So you have the component, which is consuming this data, and you have the data in some source, perhaps remote or not. And what happens is that there's some kind of system, like polling system or whatever, that's going to request the data. Do you have data? If there's no data, gets no response, then asks again, and then there's data, and then they get the data. So you need to have some kind of polling mechanism or a way to triggering the fetching of this data. In push systems, you have the data source, and every time there's a new data, it's just going to deliver it to the component. So both of these have trade-offs. Like in one hand, you need to have a pooling system for the pool. So you need to be able to have your client or your component in this case figuring out if it needs to get data and figuring out how to use the data, and the data has no idea where it's going. The other one is the push, where the data knows exactly where it should be and tells the client how to do it, but then the data is unaware, the data source is unaware of the state in which your component is. So maybe the component is not ready to receive that, or maybe the updates are too fast for them, and then you have situations like back pressure, or where you can get into situations that the component is not being able to handle, so you can have loss of packages, you can even have your system to crash. As a second way, you have this hybrid moment where we put the two paradigms together, which can be referred as push-pull, can be referred as push-then-pull. They're essentially the same. But the data, in this case, is going to notify the client, oh, I have a new update. And then the client's going to say, oh, please, give it to me whenever it's ready. And then it's going to receive the data and then update cascading down. So if you're just to be very explicit, the pull system is a system you are more used to with React, with the use state. So the component is the king of the data, knows everything about the data, and the data source doesn't really know where it is, which is why you have that tear down re-rendering mechanism where every time there's a new data, because nobody has any idea where it goes, the component just, okay, start again, and comes back. And the push then pull is what we know as signals in this case, because the signal has a subscription mechanism where the data that is coming back is able to notify every single piece that in the system that is using that data, and then notify those clients that are going to run the effects. So to summarize that, the push and pull is what makes things reactive. So because to have, like, if you're like an extremist about reactivity, to have a reactive system, you need to have a way for the source communicate to the component and one of them being aware of each other. That's why you might have seen in social media some kind of reactivity extremists saying that React is probably not entirely reactive and so on. I'm not here to get into fights with anyone, I'm just, please. So the signals are an implementation of push and pull. Does that mean that every push and pull system is a signals based? No. It's just one implementation. And the signals make the reactivity of a push and pull system fine-grained. So that's the relationship. But that doesn't tell us the full story, right? Like we now understand how it behaves, but there are requirements that need to happen in order for it to be considered a fine-grained reactivity system. And like, again, the extremists can get into debates for hours and hours, and I needed to fit an explanation in this slide, so I have two things for you. The first one is efficiency. A fine-grained reactivity system, by definition, is efficient. It's going to execute only what needs to be executed and not more. And the second one is glitch-free. The glitch in this case is not a bug per se. It's not like any kind of bug. The glitch is this very specific moment where your system may show an intermediate state. That means that, for example, you all here most of you have used before GitHub, right? Yeah? Have you ever merged a pull request and then you go back to the pull request list and then that pull request that was merged, like you had 10 pull requests, you merge one, go back to the list, the number shows 10 and the list shows 9? Yes? So that's an intermediate state that you got some state tearing because the list is already on the updated state where you only have 9, but the little badge over there is stuck in a state in time yet and hasn't updated. So this is a state, this is like what a bug is when you have the glitch, but you can have little glitches where one component is lagging behind the other one and hasn't updated entirely. So in a sense, it's like a transaction. Like once you update the state, you need to update everything that depends on that state and so on. So to recap, push and pull, then you implement push and pull as signals, and then you land to fine-grained reactivity if you're able to build a system that is efficient and glitch-free. And then you have the question about, can you achieve fine-grained reactivity without a push and pull, though? Not that I'm aware of. I haven't seen one. And we can talk a little bit about it, because even if you cache very aggressively your code, it's still not fine-grained. Like, for example, let's take this basic React component where you can render the whole stuff, and you have the button. So if you click the button, you're only updating the thing in that paragraph right there. You only update the count. But the code that executes is all of this. So you re-execute all the body function and you re-render the entire template. So in this case, it's a very small template, but it could be a bigger one, and you still like recalculating everything. On a signal-based system, when you have the button and you click, the only thing that gets re-executed is the value over there. And that's why you can see the first difference between them is that it's a function. So the value actually doesn't exist on the template. What exists in the template is a getter of the value. So when my little data source there says to me, there's a new number for count, that count function is going to get the updated value without needing to render the whole thing. But in my slides, I can do whatever I want. So I'm going to show you in real code this little comparison if my thing behaves. Yeah, cool. So here I have, what? Yeah, cool. So back to it. We have now two components side by side. And what we got here is, in this case, I have Solid.js just as a representation of signals because the one I'm more comfortable with. And in the other one, we have React. So should I make the font a little bit bigger? So the logic itself is not that important. What I want you to see is that when I render the wrapping component, I do some work, I create some state, and then I have a component A that receives a count and a component C that receives a count. Once the component A is rendered, it does some work, it renders component B and passes down the prop, and then component B does some work and shows you in the DOM what it received. Component C does a similar thing, it renders something, calls D and passes the click handler, and then D renders the click handler. In the same way in Solid, you have the same thing, A and B, then B, and then C and D, okay? So here we render it, both of them, and as you can see, when we are rendering them for the first time, everything runs. Cool? Now, in this case, oh, and I forgot to show you, this is even so using the compiler and whatnot. So it is doing a lot of memoization as well and all that stuff. So back to it. Now, once I increment it, again, I'm just changing the count. So if I click on the increment, I still run all the things because I'm actually tricking the compiler in terms of because I'm passing down the props like that, I'm essentially signing to the compiler that every one of those components depend on those things. And then on this side, I re-render, I load everything, all of them render, but then as I update, because the value doesn't exist, I don't run any body of the function ever. So it's only like that little count over there, that's the getter, and it's not here. So that little count is the thing that gets updated. So right here. So I have this props count, and then every time I'm changing the value, incrementing the value of count, it's signaling to my component that this thing needs to be updated. And now let's hope that I can pull my slides back on and things don't go kaput. Awesome. Yeah. So, and that brings me to one of the things that I consider the golden rule of DX is that if we get the good defaults, we don't need to write code for the frameworks to work. And so if we have the good defaults, we have good code, and then we can focus on the good UX in this case. So congratulations, you're signal experts now, which means we can dive a little bit deeper, because knowing what signals are is right now just scratching the surface, because now we have a bunch of frameworks and a bunch of tools using signals. And as I said in the beginning, not all signals are the same. So remember this? So you have pull, push, and push and pull. So all signals are push and pull. That is still true. But we have different flavors of signals. We have lazy signals and eager signals. The lazy signals is, let's take, for example, you have two parent components in which your other child component depends on. So this is something in reactive systems that it's like a very distant simplification of what we call the diamond problem, where it's a very quote-unquote simple problem to have, but it's one of the toughest ones to solve in reactive systems, is when you have one component that derives from a second one. You have one component, one in the middle that's derived from that one, and then you have a third one, but then that third one has also a second dependency, so you need to figure out what is the right moment to update the child, the last child, in order to not cause an intermediate state. As we saw, intermediate state is the domination for a reactive component. So what happens in a lazy system is one of them, the mom in this case, updates. And then the child says, okay, give me the update. But then the mom holds on that update until the dad is able to say, no, no, I don't have anything, or it has, but I don't have anything. And then the mom sends the update. So this is done by the means of a scheduler. And so pretty similar to like even on pulse systems in this case. So the scheduler is going to determine that your signals are going to update cascading down like step by step, or level by level. So in that case, you don't fall into the trap of having intermediate states being passed down to your child. It's always going to update all of the same time, and then all the same time, and then all the same time. An eager component, in that case, the child, the mom says, I updated. And then the child is going to say, okay, give me. And while the mom is sending the data, is already, the child itself is going to poke the dad and say, yo, you got an update. And then the dad's going to say it doesn't. So in this case, there's like this inversion of control where the child is actually going to trigger the parent component to let it know. So that's why this one is eager, is considered eager, because the child is actually pulling the updates straight from the it is going to trigger the parent into act on. So in another real code example for this, we have this one. No worries, I got it, and I just need to find my mouse, and there's a screen, cool, and bring it back like this, and that's the wrong one. Awesome, cool. So in this one we have, where is it? This one. So this is like a very distant implementation of what Solid is. So it has a few generators and it is going to update. It was created by one of our core members, Milo. And it's something that we use even internally to check how how we solve this little diamond problem. So if you can see, we have a tree, and this what's going to do is we are going to walk through the reactive system of Solid step by step in a paused manner. So in this case, I'm going to trigger the first update on A. As you can see over here, A just updated to 1. And that's going to then notify C. And then C is going to enter a state we say check. So C doesn't know yet if it needs to update or not. It needs to go up there and check the state in which its both parents are. No, sorry, again. C entered in a dirty state because it knows A updated. And because C knows their cache is dirty, they need to update. D being a direct child of C, doesn't know if it needs to update because maybe the changes don't trigger a change of value in C. Same happens to F, and then G also enters this check state, and because G entered, H is going to enter as well. Once that happens, C and F trigger C triggers B to update, and then C can update. And then once C updates, D knows it has to update as well. So C goes clean again, and which means it's the right time for D to update. And then D updates and goes clean. Meanwhile, F receives the data from A, and then G becomes dirty because F needs to update. F goes clean, G updates, H is dirty, one goes clean, the other updates, both of them are dirty. So that's like the step-by-step on how Solid solves. And if you are very attentive, you notice that all these steps, there is a little bit of scheduling in this. And that's something, please hold on to that. The point is that if we have the easier, it's kind of, if you have eager, it's a little bit easier for us to reason about as users, because then we know that the child components, the component we're actually seeing at the DOM, and then it goes poking upwards. And this enables us in Solid, because Solid is the only one that's eager, to have something different than the others. Like, for example, while all the other frameworks have something to create a tick on it, or a flush sync, or an X tick, which is something you actually tell the scheduler, okay, so at this point, you stop scheduling and you give me the value that I want. Okay, because all the values being lazy or pull, all the values they get scheduled to render it once only. In Solid, it's the other way around. So in Solid, everything is either happening in real time, or you need to manually batch them. So you need to manually say these two signals are going to update together. And the point of that, it makes it easier for you to reason about your code, because there are only two kinds of developers. And now I want a show of hands. Which ones of you use console log as a debugging tool? So that's the first kind of developer. You know what the other kind of developer is? The ones who don't raise hands. So in this case, let's say we have this little component there that creates some data and then creates this derived state from that data. So now I have a counter and I have a double counter. And whenever I update the count, I'm not sure if this is propagating to the rest of my system, which means that I need to log it. And then I'm going to log it. Like, for example, in a lazy system in this case. So this is Svelte, which Svelte has its own implementation of, it's an implementation of signals. And I'm bringing Svelte because it's very, very similar to Solid. To the point, the only difference is that they decided to go lazy. And I'm going to show you what that means for you debugging your code. So whenever you you increment that, you're going to log. So right now, as you can see here, the value is 0. I increment, my value over there is 1, but my count says it's 0, my double count still 0, and my log says the DOM is also 0, though I'm seeing it is 1. Then again, the DOM says 2, but it says that the DOM says 1, and the count, so you see the count is always a step behind. This means that the console log is getting to my event loop and being executed before my system gets updated. And that's because it's lazy, it's scheduling. When you get to an eager system, what happens is, then let me open the log. Cool. This one, and clean, and make it bigger. So in this one, you see here, I have the count as 0, and as I click it to log, I get the actual value of my signal, I get the double, that's already doubled, and I get the value of my DOM. And it just keeps working because there is no tick on it, it's not scheduled. So that's why, in my opinion, eager signals are easier to understand once you are hitting the user land. So if it's like that, I already pointed out to you that the reason why you implement lazy is because of its consistency. So it's a little bit trickier to make sure things work on an eager system. And most cases than not, this kind of accuracy is not like the biggest deal breaker. The thing is, there is actually something that also determines the memory consumption profile and how performant your code can be based on the dependency graph of your code. So if your component tree is very deep or very wide, in this case, if it's very deep, it's particularly good for lazy because of the way the lazy operates by layers. It's going to save a lot of execution time by not going up and down again. So this is really good for lazy. Lazy is really good for deeper component trees. Meanwhile, on eager, it's good for wider component trees. And the reason that we go eager on solids because eager, the wider is it's more close to an abstraction of most of the applications that we have on the web. Like we don't have, and when I say deep, is not like having a bunch of components. It's actually having components with derived state from the other. So it's not just passing down, but calculating stuff on top of your parent's code. So most of the components are wide. You have a bunch of states and you cascade down like 1, 2 layer tops. But the thing is, and I mentioned that in the reactivity, is that there is a little bit of scheduling because Solid actually has a hybrid model because pure effects are run eagerly, but derived effects are run lazily. And that's only something that goes like very, very deeply because the profile, the memory consumption and the performance profile of lazy in the very beginning when you have a smaller tree tends to be better. And then internally, Solid is able to do some scheduling to make it a little bit faster. But as I showed you, to the end user, it is eager. So eager by default and is scheduled for efficiency. And that's about it that I had for you. The last thing is, if you got curious about Signal, we do have the Solid Hack coming on with some prize monies. They start on October, and everybody is welcome to play around. You don't need to be like a super solid developer and whatnot. We have a bunch of like ports from React libraries, so that's actually a nice exercise if you just want to play around with signals and see how they go. And with that, thanks a lot, Alicante, and I'll see you on the hallway track or tomorrow. Bye.